This is our MAS 3105 final project. We chose to do our final project on basic applications of linear algebra and computer display optimization. Here I have a basic block diagram showing how a microprocessor sends out a display matrix, which is then sent to a digital processor and output to display. The digital signal processing is far more advanced than the nature of this video. Our primary focus is actually going to be on the display matrix itself that is output from the processor. Here to explain this in slightly more detail is Grady Sassnett.
We're going to give you a brief description of how your computer controls your display. Here we have an n-bit processor core, which outputs to an n by n video matrix. The n by n video matrix inputs to a digital signal processor. The digital signal processor then outputs to a m by n display matrix. Our m by n display matrix controls our video display with m by n pixels.
Although this explanation of digital processing as far as display output is concerned is grossly oversimplified, what we really need to take from this is that the processor sees an m by n matrix with binary encoded data as an input and an output as far as any display is concerned. Here I've created a 7 by 7 matrix with a very rudimentary binary encoded image into it. In case you're having trouble seeing it, I've actually highlighted the image in the data so you can see how it looks on the display. This will be important as we do operations to change it. Here to explain one such operation is Theophilis Rogers.
Simply trying to demonstrate a simple way in which linear algebra can be used to improve the efficiency of our processor. First, to map a 1-to-1 n by n video matrix in memory that will take approximately n times 3 clock cycles just to rotate the display output of 90 degrees. Instead, common software such as an Adobe Reader will do the same rotation of 90 degrees by taking the transpose matrix, which can be done in approximately n times 3 clock cycles. As a result, improving efficiency and not bogging down your processor.
Once again, let's look at our rudimentary 7 by 7 binary encoded image matrix. We take the transpose of that matrix and it will rotate the matrix counterclockwise in the same way that an image is rotated on your screen when you hit the rotate counterclockwise on basic programs such as Adobe Reader. Here you can plainly see we've accomplished something using such a simple linear algebra operation such as a matrix transpose, where all we do is swap the rows and columns. But this will produce an entirely different view on an image in your display data. Once again, for clarity, I'll highlight the image just so you can see how the picture rotated seamlessly with a simple basic operation that took considerably fewer clock cycles than it would to rewrite the whole matrix. Here to give you another example is Lamond Bruce.
Okay, I'm going to describe another way linear algebra can improve the efficiency of a motion picture. Most rapid changes in video occur in a sideways or vertical scrolling motion. Once again, to change the video output in memory will take n times 3 clock cycles, when usually only 1 or 2 rows or columns are really changing. Instead, writing just one column or row to memory and using the elementary row or column operations, interchanging rows or columns, the same video scrolling effects can be accomplished in n times 3 plus n clock cycles. Once again, improving the efficiency of our processor.
Since most motion is scrolled either left to right or up to down, and as a nature of most mechanics, an easy way to optimize video and movement is to simply do elementary row operations. The row or column interchange is the most commonly used. Here we have a very basic example with our rudimentary 7x7 matrix where we simulate a movement within the image by interchanging rows 5 and 7. Here with the image outlined, you can easily see that we rapidly, with a single operation, made our rudimentary image go from happy to sad by doing nothing more than the elementary row operation interchanging rows. This ends our project video. These are actually only a few of the possible examples of using linear algebra for display optimization, but hopefully this was informative and will make you want to learn more about how linear algebra is used in video signal processing.